This is the presentation talk for the Lunar Technology track, and our first speaker is going to be Marcus Collier-Wright. Am I saying that right?
Collier-Wright.
Okay. He's co-founder and CTO at NeutronStar Systems, UG, and he is going to talk to us about SUPREME, an advanced electric propulsion for lunar logistics. Take it away, Marcus.
Thank you very much, Ben. So I'm going to share my screen, and please let me know that when it's in full screen mode, it's going okay. You can see that?
I sure can.
Fantastic. Right. Well, thank you very much for having me, Ben, and for your help in organizing the conference. I'm really happy to be presenting at the Lunar Development Conference. My name is Marcus Collier-Wright. I'm co-founder and CTO at NeutronStar Systems UG. And today I'll be talking about SUPREME, which is an advanced electric propulsion system and its impact on lunar logistics. Just to give a brief overview of the presentation, I'll give a quick background of the company, explain the need of lunar logistics, and introduce applied field magnetoplasmadynamic thrusters as the solution, how high temperature superconductors enable them, and how their combination results in what we call SUPREME technology. I'll discuss briefly as well the impact on lunar missions, and then wrap up the presentation with the major conclusions. So first things first, NeutronStar Systems is a startup. We were founded last year. We're based in Cologne in Germany. And our main focus is the production of disruptive electric propulsion systems for high power space missions based on high temperature superconductors. The company was born with the support of three main entities. The IRS, Institute of Space Systems at the University of Stuttgart, with a wide and long heritage on electric propulsion research and development and testing facilities. Absolute System, a French SME with a specialization on cryogenic systems for space, including ESA qualified facilities for their integration and manufacture. And PI Solutions, a consulting company specializing in business innovation, project management, and high temperature superconductor technology. Our background is mainly based on two European consortia we put together for European projects. The first one called SUPREME, for a superconductor-based readiness-enhanced magnetoplasmadynamic electric propulsion system. This was coordinated by PI Solutions, which laid the foundations for NeutronStar Systems, along with our main partners, Absolute System and IRS Stuttgart, as well as Teva as another major partner of ours, a superconductor producer in Germany. Airbus and the DLR were also involved in the consortium, and overall we had 11 SMEs and research institutes around Europe. Unfortunately, this project did not get funded. The second project, which we contributed to as NeutronStar Systems, is called MIST. And this is also looking at superconductor-based space applications, but this time for a re-entry shielding system. Again, with Teva, Stuttgart, and Absolute System in the consortium. This consortium is being coordinated by the University of Leuven in Belgium, and has 5 other leading research institutes in Europe. And this consortium was granted funding from the European Union under the Horizon 2020 FET Open program, 3.4 million euros for the project, which will be starting in October. So we're really looking forward to that. So the need for lunar logistics. I don't need to sell the lunar economy to you guys. You're all part of this conference. You know where the market is going. There's a lot of activities taking place now to set up the lunar economy and develop new capabilities, being led, of course, by the Lunar Gateway from NASA, which will launch in 2024 and forms the first part of a series of steps aiming to get towards Mars. But this will also enable a lot of new competencies in areas like in situ resource utilization, lunar terrain vehicles, habitation modules, and leading towards establishing a human presence at the moon by 2028. At least that's the objective. And now building on this are now a lot of private and commercial activities also looking to exploit the moon. We have, for example, the lunar mining outpost from Trans-Astronautica Corporation, who I believe are presenting later today. I know of another company who are looking to generate power on the moon. So there's a lot of activities now going towards it. But all these activities will need some sort of logistics infrastructure to support and sustain them, to deliver large amounts of cargo, such as food or equipment or materials, which will be needed to perform these activities in a sustainable way over a long period of time. People have started to realize this. There's another company we are well acquainted with called the Cislunar Space Development Company. They are looking at setting up a space tug for transferring cargo between the Earth and the Moon. And I think it's now widely understood that this cargo logistics network is required. So what options do we currently have to transport cargo to the moon? I mean, there's a lot of approaches, but essentially I'm going to look at two main ones in this presentation. So first we have a direct trans-lunar injection launch, where we launch your cargo transfer vehicle, or CTV, directly into trans-lunar injection orbit, which then completes its journey to the moon. Now the advantage of this is that we have a short transfer time and a low delta V of about 0.9 kilometers per second after the launch. However, there's a very high launch cost because you need to launch very far away, and the cargo payload size is limited by the launch vehicle capability. So if we look at current launch vehicles, I believe this maxes out at about 20 tons for the Falcon Heavy. And consider this 20 tons has to include all the spacecraft supporting subsystems, as well as propellant and landing of the payload on the moon. Then what you can actually deliver to the moon surface is significantly reduced, around about 8 tons. So direct translunar injection is an option, but preferably for smaller payloads, especially those which are time critical. Second option is to launch the cargo into low Earth orbit and then transfer it to the moon with in-orbit propulsion. So with this option, we have a much higher capability for cargo. The Falcon 9, for example, can go for 63 tons to LEO. And this also minimizes the amount of fuel that we need once the spacecraft is in orbit, especially if we're using electric propulsion. The trade-off is that we have a longer transfer time and higher delta V post-launch. However, this is really one of the only options when the cargo payload is too large for a direct translunar injection. Now, this was studied already in the past. There was a mission architecture was analyzed by NASA Glenn Research Center, Aerojet Rocketdyne, and Lockheed Martin, and they compared an electric and a chemical system. Now, their baseline configuration was an approximately 70-ton launch payload, and for this reference mission using chemical, you needed 43 tons just to get to the moon. And when you look at all the other mass budget that you need for the supporting systems, this only led to just about 12 tons of cargo to be delivered to the surface. So from a 70-ton launch mass, only 12 tons of cargo, it is really not great figures. They also then looked at electric propulsion, and this considered Hall effect thrusters. And this enabled the delivered cargo to be nearly doubled. And not only this, but they also considered a reusable orbital transfer vehicle. So therefore, there's even further improvements on the mission economics. And this is showing really the attractiveness of using electric propulsion for this kind of mission scenario. What you might notice is that they have a very high power input for this of 600 kilowatts. To understand why, we need to have a look a little bit at the fundamentals of electric propulsion. So what you can see from this chart is that for electric propulsion systems, you generally have a trade-off between thrust and specific impulse. So if you want to operate at a higher ISP and therefore use less fuel, then you're going to have a lower thrust and your transit times will be longer. But what you notice also on the y-axis is that it's not just thrust, but it's thrust per power. So at a given ISP, we can actually increase the thrust by providing higher power to the system. Now consider a large cargo mission. You can't really get away with really low thrust because it would just take too long. And the only way to overcome this while still having higher ISP and low fuel consumption is to go to higher powers. And this is why they looked at 600 kilowatts as a baseline for this mission. With a higher power input, the necessary thrust levels to ensure satisfactory transfer times can be provided at a higher specific impulse. And in that way, we can achieve both fast transfer times and fuel efficient ones. So we can conclude that high power electric propulsion is needed if we want to transport these large cargo masses at a cost efficient and time efficient manner. However, the current capabilities of current technologies are not suitable for higher power missions because they don't scale well and they rely on using xenon. So really we need an alternate electric propulsion technology. One such candidate is the applied field magnetoplasmadynamic thruster. So this thruster is formed of two electrodes, an anode and a cathode. We then have an insulator between the two and we feed a current between them. And this forms electric field. And when we feed then a propellant gas in between, this is ionized and forming a plasma. Now with this plasma is now conducting the electric current from the anode to the cathode, and then we have a self-induced magnetic field being formed. And this leads to your first acceleration mechanism of the thruster, which is the self-induced field. We then, in an applied field magnetoplasmadynamic thruster, we take an external electromagnetic coil, we feed a current to that and generate another magnetic field, and this leads to even more acceleration mechanisms, which we call the Hall acceleration and the swirl acceleration. And there's a fourth mechanism which accelerates the gas based on the thermal expansion of the hot plasma. And this is a technology which has been around for a long time. It's been researched for over 60 years in 6 different countries around the world. This started in the early 60s, based in Germany, and there was then a lot of research done in the USA during the 60s. The Japanese then started to look at the technology, and they performed the first flight experiment of the technology, flying it in space. Then there was again some more research done by the Americans and by the Japanese, and also by the Russians, with 2 further flight experiments taking place. However, after 1996, there was a little bit of a slowdown in the research. No new prototypes were built until 2010, when 3 new prototypes were built, 1 in Italy, 1 in Germany, and 1 in Japan. And since then, there's been a real renaissance and re-interest in the research, with 3 further prototypes being built. Most importantly, 1 in China. China is now looking very strongly at the technology and putting a lot of money into it. However, the most advanced prototype that exists today is the SX3 thruster, which is based at the University of Stuttgart, our main scientific partner. This thruster is a 100 kilowatt class thruster, which is really quite high power. But 100 kilowatts only weighs 13 kilograms, which is extremely lightweight. You look at the X3 Hall thruster, which is being developed by NASA for future exploration missions. This is also a 100 kilowatt thruster, and that one weighs 230 kilograms. So you see there really the scalability and suitability of this technology for high powers. The problem is that the electromagnet is extremely large. It consumes 285 kilowatts of power and weighs 150 kilos. And this is the showstopper which is preventing it from flying. Nevertheless, it's achieved some very, very good results. It's achieved 62% thrust efficiency, which is a real breakthrough for MPD technology and is competitive now with the Hall effect thrusters that are on the market. And what I want to show you on this slide is the importance of the magnetic field strength. I've taken 2 data points at 100 and 400 milliteslas. So a quadrupling of the magnetic field strength. And you see as the thrust efficiency is much higher, we can operate at a much higher voltage and therefore a lower current, which means that the lifetime is extremely increased. And what this means is that we might have a much higher specific impulse and much higher thrust. So it's beneficial really for the thruster operation. So what we need to make AF-MPD thrusters attractive to fly is a high magnetic field and a replacement for the copper electromagnet, which is extremely heavy and takes a lot of power. The solution is high temperature superconductors, or HTS. HTS have a very high current density and 0 electrical resistance, and this makes them extremely lightweight and suitable for generating strong magnetic fields. Now, in the 1980s, several materials were discovered with critical temperatures above 77 Kelvin, the boiling point of liquid nitrogen, which meant that they became superconducting at fairly high temperatures. And this, in turn, drastically reduced the requirements of the cryogenic systems needed to achieve superconductivity, and positioning them as really suitable for space applications. Not only this, but HTS are now a fully industrialized technology. They have reached technology readiness level 9 in several areas, such as healthcare and power distribution. This is a picture from TEWA, one of our partners in Germany. They're the largest superconductor producer in Europe. They have a modular production architecture based on industrially mature processes, such as physical vapor deposition and electron beam evaporation. The production of HTS cables and tapes is now very cost efficient and robust, and it produces a high yield and a high quality of tape. TEWA, for example, have a capacity of 120 kilometers per year of tape, and these superconducting tapes are now available commercially at very reasonable prices because they've achieved economies of scale. Because they have a high current density, they're very low mass and 0 power losses, they're actually very, very suitable for space applications. They can be used in several applications, such as power transmission lines, radiation shielding, re-entry shielding, superconducting magnetic energy storage. There's a lot of applications for superconductors in space. And the one that we're looking at is in electric propulsion. And this is where we come with our concept, SUPREME technology. SUPREME stands for superconductor-based, readiness-enhanced magnetoplasmadynamic electric propulsion. So I'm just going to call it SUPREME to save us all some time. Our concept has 5 main subsystems. We start with a propellant supply and a power processing unit, which are fed into the discharge unit. Here is where the propellant is ionized, forms the plasma. The applied field module contains the superconducting coil and provides the magnetic field to accelerate the plasma And we finally have a thermal management system to keep everything at the suitable temperature. Now, by replacing the copper electromagnet with a superconducting one, we can reduce the magnet mass by a factor of 4, the power consumption by a factor of 300, and increase the magnetic field strength up to 4 times, which means therefore that we have much higher performances and much longer lifetimes. And this really overcomes all the problems facing AF-MPD from going to flight. We also have a very wide range of operation, a wide scalability to different power classes, ISPs between 2,000 and 8,000 seconds, and a wide range of different thrust operation as well. To put it into a little bit of context with the existing propulsion systems on the market, we look at 2 metrics: specific impulse and thrust. So Hall effect thrusters for electric propulsion provide a relatively high thrust at a low specific impulse. Gridded arm thrusters provide a high specific impulse, but at a lower thrust. And both of these technologies are quite limited to the respective area of this graph. Whereas with Supreme, we can provide a high specific impulse, we can provide a high thrust, and we can actually tailor the operation of the thruster for the specific mission application. Overall, we have 5 key competitive advantages with this technology. The first being a wide propellant flexibility. We can operate on argon and ammonia, which are 2 orders of magnitude cheaper than xenon. And we can also operate in chemical hybrid electric propulsion systems with single propellant system architectures. The technology is very simple and robust, and is backed by over 60 years of research heritage in 6 countries around the world. It's highly scalable. We can go up to higher power classes with minimal mass and volume penalties and scale the thruster over a wider range of power classes than any of the competitors. And it's widely throttleable, so we can be applicable to many different mission scenarios and actually optimize the thruster performance for specific orbital transfers. If we go back now to the chart I showed you earlier with the fundamentals of electric propulsion, what I want to show you here is with the red circles, the Hall effect thruster data points, and with the blue circles, the gridded arm thruster data points. Both of these are sort of quite limited and quite restricted to certain areas of this chart. And with Supreme, we can access this entire blue area. So we have a very wide operational range, and this makes us applicable to several different mission applications, including cargo transfers. So if we look again at the study, which I mentioned earlier in the presentation, for transporting cargo between LEO and low lunar orbit. And this time we will compare the Hall effect thrusters, which they considered, with our technology Supreme. So for this comparison, what we did is we fixed the landed mass and the cargo delivered to the surface in order to allow for a comparison of the mission cost between the 2 technologies. Now, the original study assumed 150 kilowatt class Hall effect thrusters weighing 150 kilograms each. Now this was a little bit outdated, and since then the X3 thruster was developed by NASA, which is 100 kilowatt class and weighs 230 kilos. So we've had to update the figures slightly. For comparison, 100 kilowatt class Supreme thruster, we're expecting to weigh 70 kilos. So just by changing the propulsion system in this context, we're saving already a ton of mass on the reusable orbital transfer vehicle. More importantly, we can operate at a higher specific impulse. So we're reducing the propellant consumption from 25 tons down to 10.9 tons. And this is using argon instead of xenon, remember, which is far cheaper. And overall, this results in a total reduction in launch mass for this mission scenario from 76 tons down to 60 tons. So if we now consider the impact to the mission cost, for the Hall effect thruster mission, the launch cost is about $309 million. Here I'm assuming $4,000 per kilogram launch cost, and the propellant cost is extremely high, $38 million. This is because xenon is very expensive and rare. It costs about $1,500 per kilogram. So overall, we have a total mission cost of close to $350 million. With Supreme, we've already reduced the launch cost with a much lower launch mass, only $245 million. And instead, we're operating on argon. And argon costs only $10 per kilogram, which means in terms of propellant cost, we essentially wiped that out. And this means that in the total mission cost comes to only $245 million. So we're saving over $100 million on launch costs just by changing the propulsion system. Another way that we wanted to analyze the effect, not only of superconductor-based electric propulsion, but a fully superconducting spacecraft, was by analyzing the payload mass fraction optimization. Now, the payload mass fraction is a measure of how much of the spacecraft is usable payload. We use the non-dimensional version of the rocket equation, This considers the thruster exhaust velocity and efficiency, the mission delta V, the transfer time, and the C parameter. We call it the C parameter. This is the mass-specific weight of the power system. So this is really important when you're considering a time constraint on a mission transfer using electric propulsion, because to fulfill a time constraint, we need a certain level of thrust. But if we go to higher ISP, we need more power to generate that thrust. And with more power, we need more solar arrays. Apologies. More solar arrays, more power electronics, and more cabling. So the whole mass of the system becomes even higher. Actually, there's an optimum specific impulse for a given orbital transfer where any further increase in specific impulse would necessitate an increase in the power system and therefore have a negative impact on the payload mass fraction. It's a little bit of an interesting idea. So to put this into a graph, we did this for the moon mission, the moon cargo transfer, using conventional technologies with Hall effect thrusters. What you can see is that for longer transfer times, we can actually operate at a higher specific impulse and get to a higher payload mass fraction, as you might expect. Now, we can compare to a fully superconducting spacecraft where the power system weighs much less. And the results are that we can achieve much higher payload mass fractions, savings up to 5% on the payload mass fraction when you're talking about a 60-ton spacecraft, and this is really significant. And this is because the power system does not weigh so much, so we can operate at higher powers and higher specific impulses without so many drawbacks. So to conclude everything which I talked about today, there's a big growing interest in lunar activities, driven by the Lunar Gateway, the establishment of lunar mining and in-situ resource utilization activities, and driven by the aim to have an established human presence on the moon within the next decade. To support this, we're going to need a logistics infrastructure to provide the necessary cargo to support and sustain these activities. And in order to provide this both cost efficiently and within reasonable transfer times, we need high power electric propulsion. And for this, new propulsion technologies are needed. The existing technologies are not scalable to higher powers. AF-MPD is a really good candidate for this. However, it's been held back by conventional technologies. However, high temperature superconductors are an enabling technology, not only for AF-MPD, but for space applications. They're industrially mature, they solve the paradigm of power upscaling, and they're very synergistic and very beneficial for space applications. And as I've shown with the analysis I've presented, Supreme offers widespread benefits by reducing the propellant costs, by reducing launch costs, launch masses, and increasing capabilities of spacecraft, not only for moon missions, but also for other missions such as Mars missions, satellite servicing, several future applications. So what we need to do now is to really flesh out some of these analyses, run some more studies, really understand the full potential of this technology. Thank you very much for your time and for listening to us. I'll be happy to take any questions. And if you'd like to get in touch with us and find out a little bit more, then please contact either myself or my partner, Manuel, and we'd be happy to talk to you further.
Thanks a lot, Marcus. That was a really interesting presentation. I'm sure there's lots of questions. Any questions out there?
I've got a question. So, have you guys already tested this in space, or has it just been ground stuff so far? And follow up to that, have you experienced or do you foresee any issues with adopting the high temperature superconductors to space?
So we have a prototype at the University of Stuttgart, which is at TRL-4, but running still on conventional technologies. We're quite a young company, so we're at the moment in the process of developing a demonstrator model. This will aim to prove the critical functionalities, that being that we need to demonstrate the use of the superconductor within the thruster to show that we can integrate it with the necessary thermal insulation, thermal management systems, and to prove that we can achieve the performances which we've predicted. In terms of in-orbit demonstrations, our current roadmap is aiming to do this in about 2025. So we're a few years off from flight because there's still a lot of technical challenges to pass, but we're quite confident that it will be worthwhile. Could you remind me of the second part of your question? Sorry, I slipped my mind.
Yeah, just in specific, if you have run into any issues with adopting the high temperature superconductors for use in, you know, space vacuum or temperature fluctuations or different things that you're going to encounter in a space application?
There's always, of course, concerns about, you know, the typical space environment, things like radiation, like the vibrational environment of launch. We're planning to take a lot of the knowledge and competencies from the fusion industry, because high temperature superconductors are used in nuclear fusion reactors. They have a very high you know, temperature demanding environment. They also have to deal with radiation, so there's already a lot of methodologies out there to protect against any radiation effects. You know, there's quench protection systems to protect the superconducting material should there be some issue with the cryogenics, for example. So I mean, we have identified issues, but for all of them so far we have solutions.
Thank you.
Okay, any other questions? Let's see, we have a question in chat. It says, what is limiting your propulsion system other than the weight of the electromagnet? Why is this technology not scalable?
Well, the technology is scalable, firstly. That's the whole point of it, and that's exactly why it's seen so much research. The electromagnet is the single component limiting it. However, it's not just the weight of the electromagnet. There's several other facets of it which are causing problems. The first being the power consumption. So I presented some experimental data at 400 milliteslas, and to operate a copper coil at this magnetic field, you need 285 kilowatts of power, just because so much of the power gets wasted as heat because of the high resistance. This also necessitates then the need of water cooling systems, which you can't really put on a spacecraft very efficiently. The other issue being that the size of the electromagnet is very big, so not just the weight, but from volume terms as well. And the third issue being that when you have still a relatively low magnetic field, as is generated by conventional technology, you have to run the thruster at a high current. And running it at a high current causes accelerated erosion of the electrodes, which impacts the thruster lifetime. So all of these three problems are solved by the single replacement of conventional electromagnet technology with a superconducting one. This reduces the mass completely. This reduces the power consumption completely because there's no losses at all. And it allows us to operate at much higher magnetic field strengths, therefore at much lower currents, which solves the lifetime issue as well.
Great. Does anybody have any other questions?
Yeah, thank you for the question, Molly.
All right, well, I guess we'll wrap up this this presentation. Thank you, Marcus. Very interesting. And no problem. And we'll see everybody else in the next presentation.
Thanks. Thank you, everyone, for your attention, and don't hesitate to reach out if you want to find out more. I'm very happy to talk to people.
Excellent.
Wishing you all a good conference. Bye-bye.
Bye, everyone.